today we're going to go over the notes from week 7, which is a continuation from the last video on business applications. But now we're going to look back at our compound interest formula and how we can use that to calculate the time that it's going to take us for an investment to reach a certain value. So if we are going to look at our compound interest formula and know that we're going to make an investment, let's say $1,000 in a savings bond, that's going to pay 3.5% interest compounded monthly. And we're going to ask ourselves the question, how long is it going to take us to get to $2,000? Now, we did some similar problems with simple interest, but the reason we didn't talk about calculating the time on compound interest until now is because what we're going to end up with, if you'll remember, the compound interest formula used your number of years as the exponent. So now we're going to have to be trying to find the exponent. And we haven't done any algebra that teaches us how to solve for an exponent yet. But we're going to be using natural logs to do that. So let's look at this problem. How long will it take $1,000 to grow to $2,000? Well, we know our R is 3.5% compounded monthly. So that is going to be 0.002916667 per period. So you just take your stated percentage rate and divide it by 12, since that's compounded monthly. And we know we're going to have 12 periods per year, but what we don't know is for how many years. That's what we're trying to figure out. So let's put all of this into our compound interest formula, which I will write it up here again. A equals P times 1 plus R to the N. But now the N is what we don't know. So A equals 1,000 times 1 plus R, 1 plus 0.002916667. And we know our N is going to be 12 times whatever the number of years are, and let's just call that T. So we know our exponent is going to be 12 times something, but we just don't know what that something is yet. So we know our A, our future value, we want it to grow to 2,000. So that's going to equal 1,000 times 1.00291667 times 12 to the T. And then let's divide both sides by 1,000. So we're going to be left with 2 equals, this will go out, 1.00916667 times 12 to the T. Then we can take the natural log of both sides. So we're going to have the natural log of 2 equals, and if you'll remember, when you're taking natural logs, you can bring that power down front and just stick it in up here. So it is going to be 12t times the natural log of 1.00291667. And now we've solved our problem by getting rid of this variable in our exponent, which is always hard for us to solve for. Using our calculator, the natural log of 2 is 0.6931447. 12t times the natural log of 1.00291667. And you can do this in your calculator as well as this in your calculator. So you're going to get 0.693145 divided by, divide both sides by this. So that will go out on this side. It'll be equal to 12t. And then once you do this calculation, that'll be equal to 12t. And then you can divide both sides. by 12, and you have t. So in other words, it is going to take you 19.83 years for the bond to double in its size. There is also another concept that I want to introduce you to called nominal versus effective interest rates. The nominal rate is what you have been seeing us state in the problem so far. That's exactly the interest rate that we're going to use when we calculate our interest, either simple interest or compound interest. But the effective interest rate is exactly what the name implies. It is the amount of interest that is actually going to be accumulating in the account. For example, if a loan carries a 4% interest rate per year compounding quarterly, then in 1 year your interest becomes 1.0406 using our compound interest formula of P equals 1 plus R to the N. So again, R was 1%, because 4% compounded quarterly is 4% divided by 4, which is 1%, which equals 0.01. And you have 4 periods in a year. So when you look at the interest that you receive, even though this states that it's 4%, once you compound it, the effective rate is 4.06%. Right there. So the general formula to convert a nominal rate to an effective rate is 1 plus R over N to the N minus 1, where R is your interest rate and N is the number of periods. Okay, so if you wanted to invest a $10,000 gift you receive, I think that would be delightful. I'd love to receive a $10,000 gift. And you have 2 investment opportunities. One, you can invest it for 5 years at 3.9% compounded monthly, or you can invest it for 5 years at 3.75% compounded daily. Which of these results is going to give you the greatest return? Well, if we use what we've already learned from our compound interest formulas, we see that option number 1 is going to go to $12,149. And option number 2 will grow to $12,061.31. So the best option for us is going to be option 1. Now in this section, we will focus on finding the present value of a future amount. Suppose that we know we are going to have, let's say, we know we're going to have $5,000 in the future, for example. So how much would we be willing to sell that option for now? So in other words, you know what you will have in the future if you hold on to your investment. But if you wanted to cash it now, what would you be willing to take for it? So in my example, I just say, if you know you can invest any cash you get today at 5%, compounded annually, we know that P, or what we can get in the future, can also be invested. So if you wanted to take a future investment and cash it out, then how would you compare that cash you got today to what it could grow to if you invested it? So if you take your P and multiply it by 1 plus R to the N at 5% for 10 years, then we can calculate our P which is our present value, and we know that it is going to be, we know that in the future it's going to be 10,000. That was our A from our compound interest formula. So we know that P is going to be 10,000 divided by 1.05 to the 10th, or P is going to be 10,000 divided by 1.62889, or the value of of holding that investment today is $6,139.15. So this number is called the present value. And we just said of an IOU, it could be anything. It could be a bond. It could be a gift annuity that you received that you're able to have the cash value in 5 years or 10 years or anything like that. And you can always calculate the present value by taking the future value and dividing it by 1 plus r to the n. You can see it's still real similar to our compound interest formula. It's just that now we're finding the P rather than the A. So P is the present value, A is the future value, R is the interest rate, and N is the number of periods. So look at the homework on those 2 pages, and if you have any questions, just let me know.